Hi everyone. For me, it's a pleasure to stay here. It's my first hardware. I traveled from Ecuador. I'm from Ecuador. I traveled until here just for the event. So I'm very happy to share this talk. This is ongoing research. I think that at the moment is at 50%. Anyway, there are interesting results. So for anyone is interested in the automotive cybersecurity world, this talk is very interesting. Therefore, I want to start with two questions. First of all, who has Kia cars here? I have a Kia car. All right, okay. So some people, and maybe someone know about what the operating system is in the head unit of your Kia car. Maybe do you know? No. Okay. Therefore, in this talk, we are going to discover a new real-time operating system. So, for everyone that want to do more research in this new real-time operating system, is very welcome. So, who am I? I'm Danilo Erazo. I am from Ecuador. I'm the founder of the car hacking village at EcoParty cybersecurity conference that I invite you. Is in Argentina. It's very funny, very cool. There are talks in English, talks in Spanish. So I recommend you. We have a village. So if do you want to hack cars in Argentina, you have to come. Also, I have a YouTube channel where you upload some hardware hacking videos and some videos about automotive cybersecurity hacking. So you are very welcome to check my YouTube channel. Okay, what is the agenda? First of all, we are going to check the infotainment system threads, the reversing about the infotainment system, the information gathering process, the hardware hacking process, the firmware dumping process, discovering the UART access, Bluetooth hacking, reversing the binary, and finally the vulnerabilities, bugs, or issues, plus the QR phishing demo. Okay, so go ahead. Okay, what about the infotainment system threads? Here we have the attack surface. Example about the auxiliary jacks. Here we have the USB ports, the touch screen, DVD, and CD-ROM. And the most important is the wireless inputs. Here we have the Wi-Fi, Bluetooth, cellular connection. And also the internal network connections, the CAN bus network, link bus network, the CAN light network, and so on. And also there are infotainment systems that are connected to through the Ethernet network. Okay, we need to dump the firmware, or we need to download the firmware. We need to look for the firmware to execute a reverse engineering process to the firmware. Search about bootloader vulnerabilities, no integrity checksums, uh, correct integrity process, and so on. Buffer overflows, operating system command injection, and so on. So we need to disassemble the head unit to look for the connections. If the head unit is connected to the wire, to the CAN bus network, to the CAN line bus network. Also, we need to look for the JTAG access and also for the UART access. It's very useful. Therefore, how many head units operating system exist? There are many, but first of all, I'm going to mention four. QNX, Android Automotive OS, Automotive Grade Linux, Windows Embedded CE. Okay, but what about the Kia Infotainment Console OS? We have that Hyundai Kia Motor Group manufacturer Hyundai cars, Kia cars, and Genesis car. So in the most of the cases, for example, in Europe, Russia, Australia, is used the Linux Automotive OS. And in United States, Canada, Saudi Arabia, India, is used the Android Automotive OS. Okay, so what about the rest countries? What about Latam? So today we're going to discover a new hidden real-time operating system. But this research had many difficulties. First of all, the firmware was not available in Kia upgrade page. Also, I could damage my car because the infotainment system cost around $600. Also, the infotainment system is without engineering model discovered at the moment, not at the sheet of the system of a chip, chips with another names and finally, no information about the proprietary real-time operating system. Okay, go ahead. First of all, the information gathering, firmware information. No worries, I'm going to show the versions in few slides.
Here
Here's the backside of the hard unit.
backup.
Okay, so we can see here the power connector, the CAN connector, the parking lights, the USB connector, and the antenna that is regarding to the radio. Okay, so here I was able to identify in the power connector what was the VCC, the GND, and so on, what act as switches, as you can see. In this case, to power on the hard unit without the car. CAN analysis, CAN IDs. When the cell phone is connected, here we have the arbitration ID 545. Okay, as you can see. The backside of the hard unit, the main board of the hard unit, and here we have that this infotainment system is supplied to Kia by Motrix. Okay, this is the display part. Okay, here we have many chips, but the main chips are the system of a chip is the TMF9200. After that, the firmware is saved in the flash WB25Q128JB. Also, we have a EEPROM. Also, we have another flash. And also, it's interesting the microcontroller, the CAN microcontroller, the M16C. There are more cheap, but these are the principal. What about the system of a chip? There's no information in internet about this chip, no data chip. So this is the unique information that I was able to recover in internet. The features about this system of a chip. I asked for the data sheet to the manufacturer, but no responses. The manufacturer is Korea Robot Manufacturing. Previously was called like Tamil Multimedia. This is a system of chip of Korean robot manufacturer that is very similar that the TMM9200. So we can see, for example, peripherals like UART, I2C, and SPI that are very useful in the boot process. Okay. Also, we have as display, memory, camera connector, and so on. The touch screen used in this case is the MXT4490, as you can see, and also there are another touch screen. The difference between the AT4183 and the AT-MXT4492 is that the MXT4492 is a capacitive touch screen, and the AK4183 is a resistive touch screen. So the MXT4490 is better. Okay. Information gathering, here we have the FCC ID for the people that want to look for or do more research in this hard unit. Okay, this is the hard unit. If you see some Kia hard unit similar, so could be probably that it is vulnerable. Okay, here we have the model, the region, and we check again that this is hard unit supplied by Motrix. Okay, so here we have the software version, the firmware version, and so on. In this case, let's do dump the firmware. First of all, let's dump the EEPROM AT24C16. And this dumping was through I2C, okay, I2C protocol. And here I was able to discover the UUID after the dumping. So EEPROM saved configuration information and also software version information and identify information. Okay, the entropy, no worries. So here we have the universal unique identifier number. In this case, I start with N150AB MA00M32685. This UUID is the UUID that also is shown in the system info in the hard unit display, as you can see, and also is printed in the mainboard. So in the boot process, when I sniff the I2C communication, I have traffic. So in the boot process, this information is recovered, is re-added by the system of chip. Okay, so let's verify this communication very fast. This communication is through a logic analyzer. So in the boot process, as you can see, there are communication. So the system will actually read this data. Okay, perfect. After that, let's dump the another flash that it is the WB25Q16. I was able to dump the flash.
This is the EV of a car.
SPI protocol. The entropy is not packet of encrypting in the most of the binary. But it's interesting because there's no SPI communication. In this case, this flash is not used in the boot process. Okay. So let's dump the big flash, the WB25Q128 with 16 megabytes. As you can see,
right now I am dumping the second flash.
And yeah, absolutely, this is in the firmware. Why? Because this is the biggest binary, and also there are like many files, compressed files, and not compressed files. Okay, here we can verify in the boot process that this flash have many interaction with the boot process, as you can see, and also in the hard unit.
Those three.
That takes around 8 seconds. In the boot process takes around 8 seconds. We have interaction. So that's the reason that here we have the second stage bootloader, and also we have the real-time operating system here. As you can see in the boot process, we have SPI communication. Okay, I don't have more information on MRBS. I was able to discover a UART access in the backside of the hard unit. So immediately I soldered the UART pins, and after that I get a shell in a car.
Let's go to start. Here I am going to start. Right now I'm going to see here all the boot process. User data, protocols information. Here yeah, this was the boot process. And from here, if I press wherever button that shadow into the CAN network, I see here the code. For example, here, radio command press down 463. For example, I press here, settings, mixing manager set current scene.
Range, Bluetooth information is very interesting because I'm going to look for these functions logs in the firmware. So before to all this, I execute a Bluetooth classic analysis because remember, in the most of the cases, in between the cell phone connection Bluetooth and the hard unit Bluetooth connection, it works with Bluetooth classic. Okay, so in this case, in the right side we have the stack, Bluetooth classic stack, the controller, the hotbar and the application, the interface, the HCI interface between the host and controller. Okay, so in this case, the phone is the master that executes the query request, and the hard unit is the slave that executes the query response to the query request, as you can see in this picture. Okay, so I discovered the Bluetooth version. In this case, is 5.4. In the frame LMP version. In the like control part, link local. And was very interesting because a legacy pattern was detected through the HCI logs. As you can see, a pin code request and also a pin code request reply and was recovered. So that means that a legacy pattern was detected because the pin code is with just 4 digits. So it means a legacy pattern detection. Okay, so what we have here that there are a paper called Cracking the Bluetooth Plane by Janib Shaker and Abishi Wald from Israel that show a beautiful technique to crack this Bluetooth pin that works in the legacy pairing mode. Okay, so in this picture we have the E22 protocols that has in the generation of the initialization key, as you can see. So it's interesting here because in run is in plain text. So what it means, the purpose of this protocol is derives the initialization key used during Bluetooth pairing. So in this case, you have here the pin inputs. We have three inputs in both cases, in the master and the slave. We have the pin code in this case and his length, in this case 4 digits. Also we have the Bluetooth device address of the claimant. Also we have the 128-bit random number that is the in plain text. So after the algorithm we have the initialization cache. Okay, pay attention to that. After that we have the E21, that is the algorithm that generates the link key. So the purpose of this is derives the link key after the initialization key exchange. Okay, so in this case we have first of all two inputs, two 128-bit random numbers. In this case we have the LK run 8 and the LAK run B, one chosen by each device. And also we have the Bluetooth device address of each respective device. The random numbers are exchanged using the KUnit, the initialization key, to secure them. So then each device runs the E21 algorithm with his random number and his Bluetooth address to produce two intermediate keys, K8 and KB, which are XORed together to form the final link key cap, as you can see here, are XORed at the end. These two keys are XORed together, okay? This link key is used for long-term authentication and encryption. After that, here we have the E1 algorithm that executes the mutual authentication. And also here's interesting because here also we have a number in plain text. So upon creation of this link key KAB, mutual authentication is performed. This process is based on a challenge response exchange. One of the device, the verifier, randomize and sends in plain text a 128-bit word called AU run. This one here, the travel in plain text. Another device, the claim, calculates a 32-bit word called SRES using an algorithm E1, the algorithm, the current algorithm. So the claimant sends the 32 bits SRES word as reply to the verifier, who verifies by performing the same calculation, the response word. If the response word is successful, the verifier and the claimant change roles and repeat the entire process. So in this case, the inputs are here. Is his own Bluetooth device address, the link key AB previously calculated in the previous process, and the random word that it is in plain text. Okay, one more. Here we have the cipher. The cipher plus is the block cipher that is used in Bluetooth to encrypt the data. Okay, so here we have the rounds. Basically, it is important to mention that because in the pin cracking is only a passive attack, is not an active attack. Why? Because first of all, we recollect some data in plain text, as you can see. 4, 5, 6, 7 is in plain text, and also if we are able to recover the in run, the LQ run A, the LQ run B that are XORed with the KUnit, we are able to execute a reverse engineering process through brute force, but offline brute force, to get with the pin, as you can see. So what is going on here? The attacker assume that the attacker eavesdrop on an entire pairing and authentication process and save all the message. So the attacker can now use a brute force algorithm to find the pin user. The attacker enumerates all possible values of the pin. Knowing the in-run and the Bluetooth address, the attacker runs E22 with those inputs and the guessed pin and finds the hypothesis for a key in it, the initialization key. The attacker can now use this hypothesis of the initialization key to decode the message 2 and 3. So message 2 and 3 contain enough information to perform the calculation of the link key. So giving the attacker hypothesis of the link key, the attacker now use the data in the last 4 messages to test the hypothesis that are in plain text. Okay, so using the link key and the transmitting AU run, the attacker calculate the SRES and compare it to the data of the message 5. If necessary, the tracker can use the value of the message 6 and 7 to verify the hypothesis of the link key used until the correct ping is found. Okay, so after that, I was able to crack the pin and the answer was 0000. So in this case, here we have the link key associated with this pin. Okay, I executed mine in the middle of attack successful because with this password Bluetooth I was able to reconstruct the PCF files regarding to the phone contacts data, outgoing calls data, incoming calls data, and missing calls. So the high unit chosen for secure simple process and require strong encryption. But so here we have in the wireshards where I was able to recover all the data in plain text. Here we have the phone numbers, the contacts. Also after that we have the service discovered. Also here have the profiles, the audio. Also here have the remote control profiles, the audio, AVDTP profile, the OBEX where files are transferred, in this case the phone contacts, the hack history, and all the previous BC file showed before. Okay, so go ahead, let's go to reverse the binary. When we execute Bingwall, we have many ground data because this is many new information for Bingwall. For in this case, these PNG files are not recovered very well, and also I was able to get after manual extraction. All this was without Bingwall. Bingwall was very grown. Bingwall version 2 was very grown. So all this information was recovered manual to execute a Python screen that look for the specific magic bytes, and so on. So here we have Bluetooth information in the firmware in plain text about the Bluetooth connections, and also here we have the ping, Bluetooth ping. It's very dangerous. So Bingwall show with me that there are part that it is a QNX for boot block. So this is a QNX. This is a false positive. Here we have the magic byte about the QNX boot block that starts with EB109000. But if you look for this GitHub issue, you are going to see that this is very false. This part of the Bingwall about the QNX is wrong. So don't trust in Bingwall. Okay. So if we look for in the binary that it is ARM architecture thumb in Big Endian, you are able to see that the offset 2D6572, remember here 2D6574 and 72. Here we have 72, 73, 74, and here we have the EB109000. And this is call function instructions in thumb mode. Okay, so finally this is not a QNX. This is a call function regarding to this another function. Okay, so this is a Brownsling exchange call in assembly. So yeah, if we decompile that, we are able to see that you are going to recheck what I mentioned, and of course this is a call mention. Okay, so absolutely this is not a QNX operating system. After I reverse all the firmware, I was able to discover all the parts. So first of all, here we have a RAR file that is regarding to the recovery, the factory reset binary. After that, we have the pre-main that is regarding to the second phase bootloader. The pre-main has one image, JPEG image, and also we have another two images that are not used. Here we have the bootloader key image, JPEG. Okay. Also here we have the bootloader binary and the CRC32 polynomial table. After that we have, the three RAR file that is the main, and here we have the three files bootloader, the kernel image, and the file system. So here we have all the information. Here we have another three RAR files. Here we have one PNG file. Here we have the certificates and also private keys and public keys, as you can see. This is dangerous because the private keys are burned in the firmware. Okay, also here we have a part about the firmware and software version, and after that we have the Bluetooth data that is in plain text. Remember the Bluetooth password, Bluetooth name, Bluetooth connections, and finally, paying attention, here we have all the displayed images. There are in total 882 PNG files that are regarding to the all displayed images that you are able to see when you power on the firmware. So all these images, all these, the home images, the settings image, and the seeds and their arrows, the numbers are PNG images. Trust me. For example, here you can see what I mentioned. Okay, after a real-time operating system analysis, here we have around 110 tags identified at the moment. We have more tags here. This is the main real-time operating system that is execute a loop. Okay, this is the central real-time operating system tag responsible for system and application initialization, hardware and memory setup, repeating set to the tag checks, event handling, and continuous manual execution for a key unit during boot and root time. Okay, this is a task loop. Okay, inside the loop, it checks system flags and system states, process events, log status, alkanes, various system handlers, and so on. Here we have also identified PNG functions, like PNG library detections. Okay, so basically, there are a lot of functions regarding to the PNG files, but these functions are about the library PNG. Okay, for example, the background color default, the transparency tune parsing, the palette tune regarding. I renamed these images with these names, but I correlationate with the libpng library, and here I have the table of the results. Here we have another more. So yeah, what is the name of this real-time operating system? The name is RTOS, as you can see in the manufacturer of the system of a chip, Tamil. Here we have three: Android Automotive OS, Linux Automotive OS, and in the final we have IRTOS. And also in the binary is born the name IRTOS, IRTOS. So the name of this is the finally IRTOS. Okay, here you have the technical information. ARM version CB, IRTOS, developed by Tamil, is writing in C, and the libraries. Okay, the vulnerabilities found at the moment was the Bluetooth pin is in 4 digits. 2 private keys are recovered from the firmware, so even attacker extract this case could decrypt and see many process. Matrix SSL 3.7.1 is vulnerable, have new CVEs. LivePNG version 1.2.29 is also vulnerable with 2 CVEs. So yeah, what is the next step? Let's test the bootloader process. So what I was able to do here, I compress in a RAR version 4, use the second stage bootloader, and after that I put in the same offset on the firmware. I don't change anything. I didn't change anything in this case. I just only was able to change to recompress the same being original bootloader second stage binary. Okay, and after that I realized that the room secure bootloader works in this first phase. But don't get up, let's continue testing more, pound or die. So as you can see here, I get a white image regarding that the operating system was not able to initialize. So After that, I realized that the first stage bootloader works very well. You know, the room boot is okay in the system of a chip. After that, the second stage loader is regarding to the pre-main that load the real-time operating system, and after that we have the displayed. But I discovered something very dangerous, that after the real-time operating system is loaded, the real-time operating system load these 882 PNG tool files without integrity process. So there are security bootloader, but if we have this no integrity process, we have here a real problem. So if you can see here, I rename all the functions, all the variables as I can, and I was able to identify the bootload process. So here we have the flash detect device. You know, in this case, only there is a flash detection. After that, we have here the log memory map, apply the memory map options. Here we have the log start of the memory map option application, initialize the primary memory regions. Okay, log memory usage, about the range, the alloc size, the total size of the memory, and you know, in the boot process. Also here we have the log memory stats, sets output pointers for system pool and end memory sites by saying on the more and weaker sites. In this case, this is the moment when the Kia logo is shown in the boot process. Okay, as you can see. After that, the core application initialization, this is the moment where the main binary is called. So in this case, this is executed. Okay, so in this case, here we have the real-time operating system loaded in the memory, and all is the vulnerability is here, principle in this part number 4, in the plain main text real-time operating system where the file system is mount. Okay, so let's go to check, because in the function main application tags, here we have that the process is, first of all, the GUI application, or maybe the UI daemon, issues standard file open calls. These open calls are executed by the operating system that reads the raw PNG bytes from flash into the main memory via the system on chip memory controller and bus fabric. Immediately this PNG library, you remember, leave PNG parse headers, the compressed iData chunks, and produce a uncompressed RGBA buffer in RAM. But what is going on here? libpng checks are don't are useful because only checks all the its image, but don't checks about the hash of the integrity of the entire image. So libpng only checks about the headers, header checksums, headers data checksums, but not about the integrity process of the entire image. So that's the problem. Okay, so I realized that the firmware is able to set a backdoor. So the proof of concept to change the home logo to with the word hack. So after that, I was able to see that. In this case, we have the hack word. As you can see, hack word. So after that, I say, hey, let's do this more danger. So let's set up a PNG backdoor. So after many failed attempts, I was able to realize that the fake image must be the same size as the original image. If the fake image that I am going to inject is smarter than the original, padding with zeros is an option. The image will not render if it is compressed. Some metadata is verified by the real-time operating system, specifically by the live PNG library. And finally, it is possible to replace any image as long as the same onset is maintained of the firmware. Okay, so that's the reason that I create this tool, okay, to automatize this infection firmware process. So here we have the normal QR that redirect to the official Kia vendor page, as you can see. Okay, this is the official Kia vendor page. So after I run my my script, I was able to basically to infect this. I was able to get the infected firmware. Okay, so in this case, I entered the original PNG part. Also, I entered the new PNG to insert to replace the original image. Yeah, the tool allow me to see the new infected image that is already in the infected firmware. Okay, here I am able to compare the hash of both firmwares.
Alright,
Now
so
let's go to check
I connected
final.
just the power connector, not the CAN connector, not the antenna, just the power connector to test. Have the K-fob, and also I have the another cell phone for a scan the QR. Alright, so I'm going to power. Yeah, come on, let's go to check.
This was the
Here
first
I
time I
have
was able to
ready
get
the
a subscription
QR for the scan, and yeah, there we go.
very happy to me in this moment.
Film, and if all is okay, if I go to settings, system, and manual, yeah, this is not the Kia manual official page. This is my the QR of my page. So let's go to test. Yeah, here we have. Where is everything? Let's go to put here open.
Yeah, and basically
Yeah,
here is
this is
my
my
page
page, bros.
coming to the Kia web page.
You can go.
Okay. Also, another way to infect, is through the USB because the previously was through flash the firmware through the SPI. So this was a hardware attack. Okay, all the bugs detected, the insecure bootloader, the integrity control is not applied to all the firmware binary, the RTOS used vulnerable libraries, a high unit private keys was leaked, the Bluetooth data in plain text, and the Bluetooth legacy parity is enforced by the hard unit. So, yeah, Kia cars affected. There are many cars Kia affected, tons of Kia cars with RTOS in the world. So, thank you so much.